Okay, we'll go ahead and get started. So all I did here was the first slide is just kind of a review of what we've done here. So if we look at this, we know a heating curve tells us, it's just a little bit smaller here. There we go. Heating curve tells us how much energy is required to heat something from one temperature to another. When you look at a heating curve, there's a couple different things that you want to make sure you notice. There's two different parts to a heating curve. So one part is where the solid, the liquid, or the gas is being warmed. So that first little section is where the solid's being warmed. Second section is where the liquid's being warmed. And then the last section is where the gas is being warmed. Okay, so that's our first thing that we have to make sure we recognize. During those times, there's a temperature change. So when the temperature is changing, you're going to use a different formula to solve for how much heat is needed during those periods on the graph. The other part of the graph is during the phase changes. So that's what these green parts are. So the first phase change is going from a solid to a liquid. Second phase change is going from a liquid to a gas. So the temperature doesn't change during those phase change parts of the graph because the energy that's still being put into that substance is being used to pull those molecules away from each other so that they can change phase from a solid to a liquid, or a liquid to a gas. Whereas in the other parts where the temperature is changing, it's increasing the kinetic energy of the molecules. So that's why it flat lines out when you have a phase change, because that energy is not being used to make the molecules move faster, it's being used to pull those molecules apart from each other. Okay, so what we're going to do here, I don't think we need to work through all of the questions on this sheet. So what I'm doing is I am going to use, as soon as I find it here, this is the review sheet that you guys have. So this is the one that's in your packet. This is also the one that is posted on Google Classroom. So unless you want to, once we go through each one of them, if you want to work through the actual calculations, we can. I think the main issue with these is getting it set up correctly. I think once people get the right part of the graph highlighted, then the calculations are pretty straightforward, as long as you remember a couple things, and we'll talk about all those as we go through here. Okay, so let me change my slide here. So what I did was I put each one of these in here. Okay, so this is number one. Again, this is from the paper that's in your packet. So this is it says changes in state calculations. So those are those heating curve calculations. So number one says how much energy is required to completely vaporize 200 grams of 25-degree liquid water. So like I said, what we're going to do is we're just going to highlight on the graph, and then we are going to, and then we'll kind of talk about how to set it up. But like I said, unless you want to go through all the calculations, we don't necessarily have to do that. Okay, so if we look at this one, it says completely vaporize. So for this one, all we're doing, for this one, it's starting at 25 degrees. So what I would do with these to start with is I would put the starting point and the ending point on the graph. Then that will help you kind of know where you need to go, where you need to stop. So 25 degrees, we're just going to assume is right here. And then completely vaporize means we're going to stop after it's gone through that phase transition. So it's not going past vaporization. We're not heating the vapor. It's just going to be completely vaporized. So that means for this one, we would need this section of the graph and this section of the graph. So this would be one that would have two steps. So we would use a Q equals MC delta T for this first part. So this would be Q equals MC delta T. And then the second part would be the heat of vaporization, which would be that 40.7 kilojoules. Okay, again, when you're doing these, like I said, there's a couple things you have to make sure of. If you are in this first section down here, You have to remember that water is in the solid state, so you have to use the specific heat associated with the solid state, and you'll have those values. You have them on your reference sheets. They're also going to be in the quiz themselves. For this second part of the graph, this is the liquid phase, so you have to make sure you use specific heat for liquid. In this last part over here, that would be the gas phase, so you have to make sure that you use specific heat for the gas. When you're doing phase changes, heat of vaporization is that 40.7. If you were doing this part right here in the graph, that would be the heat of fusion. That's that 6.01 number. Last thing you have to make sure you remember is that when you solve for Q, Q is going to be in joules. So you have to go from joules to kilojoules, like I showed you in those couple videos and in some of the notes that we did, before you can add all of those up together at the end. Okay, any questions on this one? Do you want to go ahead and work it out, or are we good with just doing the setup? Okay, nobody says anything. I'm going to assume that you guys are okay with the setup. I did post the answer key for this, so you'll be able to see my work on Google Classroom. If you open that sheet up, I have it all worked out so that you can see what all the steps are. Okay, so then number 2, how much energy in kilojoules is required to melt 150 grams of minus 18-degree ice and bring the liquid up to 25 degrees. So on this one, if we're starting at minus 18, we know that first flat line is 0, so we know that we're going to start down here at the bottom. Then we're going to bring the liquid up to 25 degrees. So we're not going all the way to the 100 mark, which would be where letter D is. We're stopping when we get to 25. So this one is going to have 1, 2, 3 sections. So we're going to do a Q equals MC delta T, and C for this one has to be for the solid. The mass is going to be the same for all of them. Delta T, remember, is always final minus initial. The second one, we're going to use the heat of fusion using that conversion that we talked about. And then the last one, Q equals MC delta T. C this time is going to be for a liquid. And delta T, we don't need that whole section. All we need is the 25 minus 0. So unless it goes all the way up to D, all you need to do is just take whatever the final temperature was. So in this case, it was 25 minus 0. So that one's only 3 steps. Okay, I'm going to go on. So stop me if there's something you want to go back to or talk about, or if you want to work any of these out. All right, number 3. How much energy is required to change 25 grams of ice at 0 degrees from a solid to a liquid? Okay, so notice there's no temperature change. So that tells me that it's at 0, and all I'm doing is just changing the phase. So for this one, I only need this one little section of the graph. So for this one, the only calculation I have to use is I have to use the heat of fusion. So I'm going to do that 25 grams, change it to moles, using the molar mass of water, and then use my 6.01 kilojoules, which is that heat of fusion constant per mole, and then that's going to give me my value for that. So that one, it is possible where you only have to do one section of that whole graph. Okay, next one. We're looking at how much energy is required to completely vaporize 15 grams of ice at minus 20 degrees. Okay, so minus 20 means we're going to start down here. Completely vaporize means all we're doing is we're taking it to the vaporization. So we're not heating it past that. It doesn't tell us, it doesn't give us a temperature above 100. So that tells us that it's going to stop once we hit that vaporization phase. So we've got 1, 2, 3, 4 for this one. So a Q equals MC delta T using the solid. Then heat of fusion for the second part. So this is 1, 2, we'll label these as we go here. 3, a Q equals MC delta T. This time C is a liquid. And then 4, conversion using heat of vaporization. Okay, again, making sure that these you have to convert to kilojoules. Don't forget to do that. And then you add them all together. Number 5, we are changing 55 grams of ice at minus 10 to steam at 150. So for this one, minus 10 is going to be below 0. And then 150 is going to be up here above point E. So it's going to be at point F, which you can't see because of our names on the side there. So on this one, we're actually going to need 5 steps. So we're going to go through all of them. So on the quiz, they're not all going to be big 5-step problems like this, but I would make sure you know how to do the ones that have 5 steps. So step 1, Q equals MC delta T, with C is a solid. 2, conversion with heat of fusion. 3, Q equals MC delta T with a liquid. 4, use the heat of vaporization conversion. And then 5, Q equals MC delta T for the gas phase. Then you would add them all up, again, making sure you convert these to kilojoules before you do that. And then that'll be your final one. So the only time that you're going past that vaporization phase is if they give you a temperature over 100 degrees. If they don't give you a temperature over 100 degrees and it says something about vaporization, then that tells you that you're stopping before it goes past that point. Okay, next one, number 6, how much energy is required to change 12 grams of water from 5 degrees to 95 degrees. Okay, so on this one, 5 degrees is past the melting point, 95 degrees is before the boiling point. So for this one, you're just going to need 1 step, and it's not even that full section in the middle. So since there is a temperature change, it's going to be Q equals MC delta T. Your C value is going to be for a liquid, and then your delta T, again, you're going to do final minus initial. So 95 minus 5. So for this one, you'd have 12 times 4.18 times 90. That temperature change, when you're doing those sections that are increasing in temperature, it doesn't always have to be that full section. It could just be part of it. So that's why you always want to mark your starting and ending points on those graphs so that you know where to start and where to end. Okay, any questions on the heating curve stuff? Okay, the last one in here, I'm not going to make you do this on the quiz, but just to kind of see that there is something that is the opposite of a heating curve, and that's called a cooling curve. The only difference here is that everything is going to be exothermic instead of endothermic. So if you remember, if you've done that video for the heating curve yet, a heating curve is endothermic because heat has to be going into the substance in order for those phases to change from solid to liquid to gas. For a cooling curve, it's the opposite. They're going from a gas back to a liquid back to a solid. So they're actually going to release heat. So those are going to be exothermic. So for these, you would still use Q equals MC delta T on the parts where the temperature is changing, but you'd have to be really careful to make sure that you do final minus initial, because in those cases, all of those temperature changes are going to be negative. Heat of vaporization is going to be negative 40.7. Heat of fusion down here is going to be negative 6.01. So on these, every value should be negative. So then you're just adding all those negative values up. So overall, for this one, if it's a cooling curve, it's going to be an overall negative value.